Section 4 of AS NZS3008 2009 version provides us with information and guidance on voltage drop requirements for cables. Now, after the first step, of course, of checking for current carrying capacity, we have to look at the actual length. This usually comes into play when there's excessive length in the cable, usually beyond 20-25 meters. We need to start checking for volt drop requirements. For customers' cables, we're dealing with the cable running from the point of supply. Now that could be at a mini pillar for underground supply, or that can be the point, also be the point of attachment. If you look at the WA electrical requirements, you'll see the variations on the point of supply. Then from the point of supply through to the meter, the meter box, the switchboard, and then from there going out to various final sub-circuits and also sub-mains. Clause 362 of the AS NZS 3000, the wiring rules, states that the cross-sectional area of every current carrying conductor shall be such that the voltage drop between the point of supply for the voltage electrical installation and any point in that electrical installation shall not exceed 5% of the nominal voltage at the point of supply. So what that means is that it's simply from the point of supply, simply shown here in the graphic, say from the mini pillar through to the end of each of the final sub-circuits, whether that be a lighting sub-circuit, a socket outlet, an appliance, and then even 5% from the point of supply through the consumer's mains, through a sub-mains to a outbuilding, and then to the end of that final sub-circuit in the outbuilding, which could be a socket outlet circuit. So it's still 5% from the point of supply to the very end of any final sub-circuit. And continuing on with that theme, it applies to commercial, industrial circuits as well. So again, from the point of supply through to it can be a consumer's mains, and then a sub-circuit or a number of sub-circuits, through sub-mains through to the final sub-circuit. We're now going to look at a new unit, the unit of VC, which is millivolts per amp meter. Now, this unit is used for the purpose of volt drop and used with the volt drop tables, which is table number 40 through to 51. So the various tables will depend on the type of cable and the type of installation and the type of installation method you're using. So the VC, which is millivolts per amp meter, shown in the little graphic here, which is actually how many millivolts are dropped across a particular size cable over a meter of that cable with an amp of current flowing through it. So this is actually the unit is actually an impedance. So it's not a voltage. The VC, even though it does have the V in the prefix for the unit, but the VC is the millivolt per amp meter. It is used in conjunction, as you'll see in the formula, 1000 times the VD, which is the actual volt drop. Now that is a voltage. The VD is a voltage. Divided by the root length of the circuit, and then the current, which is the maximum demand or the current draw for that particular circuit. Also, you'll see in section 4 of the 3008 that it provides you with the formula which is VD. Now this is just a transposition of the other formula, of course. We're here VD, which is the actual volt drop in volts. Is determined by multiplying the length of the circuit root length times the current, which is the maximum demand or the current draw on the circuit, on the appliance, times the VC. Now the VC, of course, is taken from the table 40, 40 onwards, which are the VC tables, which are three-phase tables. VC, and then divided by 1,000, which gives you the actual volt drop that will occur on that cable when that cable is drawing its maximum demand, or the full rated current for that circuit. In section 4, as you read through, you'll also see other methods of determining volt drop. In this particular case, volt drop from the circuit impedance, where they're using the two tables there, which is the resistance of the table and the resistance of the cables for over a particular length, and the impedance of the cables. It is. We also have the formula here for cable operating temperature to determine the actual cable operating temperature, which is a more accurate use of the volt drop tables. However, we won't be going to this extent. We'll simply be sticking with the VC calculation, and won't be going any further than that. There are various software packages that allow you to calculate the current capacity and volt drop and so forth, and do maximum demand calculations. Now these software packages will generally use the more accurate methods, using cable operating temperatures and so forth. So if you do find that when you're using a software package, that your manual calculation is slightly different, that's the reason why. It's because they're using the more accurate methods. Again, just another example of some another application for volt drop, which is using from the load power factor. Then we have this formula here, which we can apply to multi-phase loads which aren't balanced.